So what are the direct measurement methods I was mentioning before? The first one is the one-port impedance measurement, then we have the impedance adapter method, an external bridge method, and then we have indirect measurements, where you actually measure gain, but the result equals an impedance, or you have to transfer it a little bit. And there is the two-port shunt through, the two-port shunt series through, and simply measuring a voltage current gain, which then equals impedance. So let's go into the direct measurement methods. So the direct measurement methods of the Bode 100 support a full impedance calibration, meaning you can do an open, short, and load calibration. And these methods in the software directly display impedance, reflection, admittance, the series inductance, parallel inductance based on a basic series and a parallel equivalent circuit, series resistance, series capacitance, the Q of a simple circuit, and the voltage standing wave ratio, for example. So where do I find these methods in the software? And this is really the first time I would like to mention that, and we will mention it very often afterwards. Under trace 1 settings, there is this measurement box, and there you can select impedance, for example. And then in the format box, that's the box below, you can say magnitude. So this will display the impedance magnitude. And then here we have this Y scale, and I did set it to log of trace 1. So this setting will display the magnitude of impedance with a logarithmic Y-axis, and this is very nice sometimes. The second trace, for example, I want to see the impedance phase, so I simply select measurement impedance and format phase in a linear scale, because logarithmic phase doesn't make any sense. All the formats we have available are shown here. So there is magnitude, you can also show it in dB if you like. You can have the phase in degree, the phase in radians, the group delay of the impedance. This is the first derivative of the phase with respect to frequency. Then you can display it in a polar form or in only the real part or the imaginary part, since we are always measuring a complex value, complex number, the complex impedance. And you can always select what you want to see. Okay, so what are these direct measurement methods I was talking about before? The one-port method. This is the simplest impedance measurement method, and it's very easy because you only have to connect the one-port device under test directly to the output of the Bode 100, and you can already display the impedance. We will do that afterwards. Then we have the impedance adapter method, where we have our test fixtures, the width and wick and the BS and C for through-hole type components and surface mount components. And there is this external bridge method, where you can build any arbitrary custom bridge and calibrate here with open, short, and load, and then measure the impedance of a device under test. We will have a look in these measurements in detail now, and the first one is the one-port method. And this is the same measurement method any standard VNA uses to measure the S11. So this is the reflection coefficient. And as with any standard VNA, this method is most accurate if you have a device under test that is very close to 50 ohms. And we recommend it for impedance measurements from 0.5 to 10 kilo ohms. So this is the range where you can get good results with not too much noise and a good accuracy. The advantage of this method is you can use it over the full frequency range of the device, in this case from 1 Hz to 40 megahertz, and you can even measure without any calibration. So it's very quick because you don't need calibration. There is a full impedance calibration possible if you, for example, connect your device under test with a cable. Then you can remove the influence of the cable or a different test setup.
Yeah, maybe there's one thing to mention. When you start up the Bode 100, it performs an internal calibration, and so if you connect the component directly to the output port of the Bode 100, usually it's quite well calibrated. So you can test this by just connecting a 50 ohms resistor to the output, and then you will see a very good phase and magnitude of the 50 ohm resistor.
Yeah, thank you, Bernhard. So what's the measurement setup? As shown before, it's very basic. It's just a device and a test connected directly to the output or to a coaxial cable. And in the Bode analyzer suite, we have to select the frequency sweep mode. That's our basic vector network analyzer mode. And you have to change the measurement of the traces to impedance and the format to whatever you want to display. Then you set the start frequency, the stop frequency, the sweep mode, and the number of points, and you're ready to go. So another point which is quite a bit confusing, but if you know why, then it doesn't confuse anymore. We have the device configuration in the Bode Analyzer Suite. And I have already clicked on this impedance reflection radio button here. And this radio button, if I click here, it now shows me the device configuration inside the Bode 100 hardware the device uses when I select measurement impedance here. So I have now selected measurement impedance here, and then the device will use this configuration for the measurement internally. You don't need to worry about that, but if you're interested.
Yeah. Some people contact us and they ask, oh, if I change my radio button to gain phase, can I still measure impedance? Yes, you can, because this radio button here is just for displaying the different configurations, but the configuration is actually selected by the measurement that Florian just indicated.
Okay, we will now already directly head into an example, and we will now analyze a power inductor. So we measure the inductance and the self-resonance frequency of a power inductor. Shielded, we have a 22 microhenry shielded power inductor from Würth Electronics here. You see the picture. I've directly soldered it to a BNC connector, and the datasheet says it has a 22 microhenries plus minus 20% at 1 kilohertz, and the self-resonance frequency is typically at 15 megahertz. So let's see what the result really is. So I can now show you the device on the test here. So our test setup. One moment, Bernhard is adjusting the camera.
Oh. Keeper got me, yeah.
Okay. Just take it off again. It's already connected to the Bode, and here you can see again our device on the test.
Yeah, it's
the camera
out of focus. It's waiting.
Out of range. I simply connect it to the Bode 100.
And we measure now without calibration for the beginning?
I will start the software. So we'll restart the software, just that we start from a clean point. Okay, let's click on the Bode Analyzer Suite, and the software is now starting up. We will see it in a second. Yeah, perfect. So this is the software screen as it comes up if you start the Bode Analyzer Suite the first time. And the only things I need to do to measure the impedance of our power inductor now is to say measurement, select impedance. Then I said I will set the format to magnitude, and I will say magnitude logarithmic. And then I want to see the trace 2, I want to see the impedance, and here the phase. And then I want to see it in 2 diagrams. And then I want to see the frequency axis, not linear, but logarithmic. And now we do already have a picture of the inductor. Let's start at 10 Hertz or at 100 Hertz to see the low frequency end of this inductor. Okay, here it is. Well, it was so quick, I'm quite impressed. Okay, I don't know what to tell you.
Yeah, so measure the self-resonance for the beginning.
Oh, thank you very much. Okay. If I now want to measure the self-resonance frequency, which we can see here, where the impedance peaks and the phase turns from plus 90 to minus 90, because the inductor will turn capacitive after the self-resonance frequency, I just take a cursor, I activate the cursor 1 here, and then I say, for example, on the phase, cursor 1 jump to 0, or I could say on the gain magnitude, impedance magnitude, I can say cursor 1 jump to max, and this is nearly the same. I now can read the self-resonance frequency here, and it shows me 15.2 megahertz.
Yeah, and you can see that this is a nice inductor because you have an incline of the magnitude with roughly 20 dB per decade, and okay, it's not in dB, but if you would switch to dB, and you see that you have a nice flat 90 degree, and you also see that it starts resistive because it starts towards 0 degree. If you would go down lower, let's say for 10 Hertz, then you will see that the phase curve gets close to the 0 degree.
Okay, let's start once at 10 Hertz, a second measurement, and then we will see that the phase starts close to 0 because the inductor works purely resistive in the beginning when the inductive part is not dominant, so then the resistive part is dominant. And then we could measure the wire resistance. Well, a very precise measurement you will only get with a milliohm meter or a DC ohm meter, because here on cursor 2 I have placed it to 10 Hertz now. It tells me 98 milliohms or nearly 100 milliohms, and as mentioned before, this measurement is very accurate from half an ohm to 10 kilo ohms, and if it's now 98 or 102 milliohms, this is not the right measurement to determine this.
But later on we will show a measurement for low impedances.
Okay.
Maybe the inductance in Henry.
Yeah. Now the second thing we want to know is what inductance does this inductor have at 1 kilohertz. So I place the cursor 1 at 1 kilohertz, I enter 1K, enter, and the cursor is there. Well, 1 kilohertz is maybe not the right point because we see that it's not really inductive yet.
Yeah, but that's what they say in the data sheet, huh?
Let's see the result. I start at 100 again to make the result a bit quicker, because at 10 Hertz it measures slower. And then I say on trace 2, format not phase, but the series inductance. And then I say I start here at 0 Henry and have a look up to 50 microhenries, and then we can see at 1 kilohertz an inductance of, cursor 1 tells me 21.6 microhenries.
Well, so okay. This is quite well within the range they indicate in the data sheet.
Well, they are quite accurate.
And what I would like to mention is that we did not calibrate the Bode 100 so far, so this is just working with the internal calibration of the Bode 100. So you can see that the calibration is switched off, and we are measuring directly with the accuracy of the device. So it's just to show, if you don't have a cable, you have a really neatly calibrated measurement device just by booting up the Bode 100.
Okay. So if there are any questions, feel free to post them immediately. But I think for the moment this is nothing special.
The special stuff will come later on.
Yeah. Okay. Perfect. So let's continue with the presentation, and I have already prepared the examples before. The same results that we got this time. The only thing I have done here in addition was to display the series part of the impedance, the resistive part, only the real part, and this equals the wire resistance over frequency, and you can see that the wire resistance increases over frequency, and this is due to eddy currents, and due to the skin effect and proximity effects in the coils. The resistive part, so the losses itself, are depending on frequency. So the next method I would like to present, or Bernhard, do you?
I'll do the setup for you.
Okay. The next setup I would like to present is the impedance adapter method, and we have introduced a special software mode in our software. That is designed for the impedance test fixtures. On the left-hand side, you can see the BWIC, that's for wired components or through-hole type components, and the BSMC, that's for surface mount components. They both offer a frequency range from 1 Hertz to 40 megahertz, and the impedance range, which is useful, is from 20 milliohms roughly to 600 kilo ohms. The reason we can't go lower in impedance in the milliohm area is because this is not a Kelvin connection measurement. It's just 2 connectors and not 4 connectors, and therefore we would have problems if you want to measure in 10 milliohms, for example, because the contact resistance of the fixture itself is with some milliohms, so it doesn't make sense to measure below 20 milliohms. How is this method working? The impedance adapter needs to be connected to the Bode 100, output to source, and channel 1 to channel 1, and channel 2 to channel 2. And now, very important, in the Bode analyzer suite, you should or you must select this impedance, this ohm sign. That's the impedance adapter mode. And then everything will be preset in the Bode suite such that you get the best results. It will also work in the normal frequency sweep mode, but you will have very low accuracy.
Okay, Florian, in the meantime, we got a question. It's a question about the DC bias dependence of an inductance. I think later on we will show the DC bias inductance of the DC bias dependence of a capacitor. For an inductance, I think it can also be measured, but it's a little bit more tricky.
Yes, you have done that already, the measurement, I think. So there are many possibilities to measure inductance with DC bias, but they all have their limitations, and they are require quite a high effort. However, if you are really interested in that method, please send us an email, and then we can tell you all the things we know about this measurement. This would fill an entire webinar itself.
Yeah. Usually the key problem is that you have a current source and you don't want to measure the influence of the current source itself. So you need to decouple the current source from your device on the test. And this usually you have to do with an even bigger inductor, which is much bigger than the inductor you're measuring. And this is the tricky part to get such an inductor. Nevertheless, we will provide this information later on. There's another question: what benefit can we have using the impedance adapter instead of soldering a component directly to a BNC connector? This can be answered quite easily. With the impedance adapter, you have a wider measurement range. Yes, so you can measure up to about 600 kilo ohms, while the other method just goes up to 10 kilo ohms. So you have less noise. The bridge adapts the device on the test to a maximum wide range of the Bode 100, while the VNA method that we introduced before, the one-port method, only provides accurate results around 50 ohms and in the range that we indicated earlier.
Okay. So the impedance adapter always needs to be compensated, because it has a small bridge inside that adapts the voltage ranges for the Bode 100 in an optimal way, and that's why we have an increased impedance measurement range with these fixtures. And you always need to compensate them before you can start measuring. So you need to do a calibration, open, short, and load calibration. And with the BWIC, the wired component adapter, it's very simple. We deliver this test board that has a 0.1% 100 ohm resistor with a very low temperature dependence on it, so it has a very accurate resistor for calibration. And you simply place the board with the short circuit side for the short calibration, or with the load resistor for the load calibration. With the surface mount component adapter, it's the same thing. The only thing is that here you have to remove the needle, or to make a distance between the needle and the electrode for the open calibration. So this can be seen here on the left-hand side. And if you are measuring very small capacitors, then it's important that this distance is, for the open calibration, is the same distance as the tooth size, or the size of the capacitor itself, because the air here will already form a capacitance, and if you don't want to measure this capacitance, then you have to remove it. And this is done with the open calibration. And here again we have the same 100 ohm resistor.
Yeah, you get about 5 of these high precision 100 ohm resistors with the adapter. If you lose them, just send me an email, or send Florian an email, and we will ship some to you.
Yeah. Okay. We will talk about calibration very often with the Bode 100, and something that is quite a pitfall are the names of our calibration. We have the user calibration and the pro calibration. If you want to understand it, it's very easy. The user calibration calibrates over the frequency range the user has set. So it calibrates at exactly the frequencies that are currently measured in the sweep, at all the sweep frequencies. The advantage of this is that it doesn't do any interpolation, and it's so useful and suitable for very narrow band probes. In this case, this is not that important, so you can also use the probe calibration. The probe calibration is a full range calibration that calibrates the frequency range of the Bode 100. So it starts at 10 Hz, goes up to 40 megahertz. And if you're measuring in a small range in between, then it will just interpolate the calibration points and interpolate for your measurement points. If the calibration does not need to compensate very narrow band stuff, then this is accurate enough.
Absolutely, and the advantage is that you can play around with your start and stop frequency, and you will never lose your calibration. While if you do the user range calibration and you start your start and stop frequency, since no interpolation is allowed, you will lose the calibration and you have to redo it.
Yeah. Okay, let's do an example. We will measure the ESR of an aluminum capacitor. Our device on the test is a 220 microfarad aluminum capacitor, aluminum electrolytic capacitor, and the datasheet does not directly indicate the ESR. It only gives us a tangent delta value at 120 Hertz, and we calculated the ESR from that, and it says 0.7 ohms, so 700 milliohms at 120 Hertz. And now we will start the measurement, so let's have a look at the test setup.
Yep.
Okay, Bernard will again do all the camera stuff, so our camera man.
The key question is, will it work nicely with this webcam? So, okay, so we can do the calibration. Maybe if you make a small screen, then we can show the calibration in parallel to the Bode software.
That's a good idea. We'll just make this smaller here. And the Bode software also in small. Okay. So, as I mentioned before, we have to go to the frequency sweep impedance adapter mode, and that's this ohm sign you can see here on the top. So I click on this ohm sign, and the software will start to work and start a preset. And now we have to do a calibration, because we cannot do the measurement without calibration. If I try to do it, it will say you need a calibration, and I select probe calibration. And the first calibration point will be the open calibration, so nothing is connected to the adapter, and I say open. Then the device measures the frequency range, and now we do the short calibration. So Bernhard is placing the short circuit board, and I say short. Okay, that's done now, and then we turn around the calibration board, and we measure the 100 ohm resistor and press unload. The good thing is you can also store this calibration to a file. If you save the Bode file, the calibration will also be stored. Of course, if you remove the cables and you place them again, you will have a little falsification of the measurement, because you have different contact resistance maybe of the BNC cables, but generally the cables, if they are good, then this shouldn't lead to a problem.
So when Florian has finished the calibration, you can just leave the resistor in. We are using a 100 ohm resistor for this calibration, so we can now check if the calibration was successful. And what looks like a crazy curve for you on the screen is in fact showing a very accurate 100 ohm, because the entire diagram is from 100.015 ohms to minus 99.99 ohms. So this is in fact a quite good result, and we can now remove the 100 ohm resistor that we used for calibration and add our capacitor.
Okay, so the sweep is already finished, and as I have done before, I will also select the logarithmic Y scaling here, and we see a capacitive region from 100 Hertz to nearly 10 kilohertz, and then we see a resistive region, so the phase is close to 0 degree, and the curve is flat, and then we see an inductive region again after 1 megahertz. So this shows us the real capacitor. It's capacitive up to a certain frequency, then the ESR gets dominant, and then the ESL, the series, the parasitic inductance, gets dominant after 1 megahertz in this case. So what did we want to measure, Bernhard?
Well, we want to measure the ESR of this capacitor.
Okay, so in this case, yes, we said we want to measure it at 120 Hertz. So I select the cursor 1, and I enter 120 and press enter, and the cursor is now placed at 120 Hertz. And this is a quite capacitive region, so it shows nearly 90 degrees of phase, and the ESR can be read if I select the format RS here on the trace 2. So that's a series resistance. Let's see what it tells. Okay, so it says 220 milliohms. But you can see that the series resistance is very depending on frequency, so it's strongly depending on frequency. And if you're doing switch mode power supply design, for example, or linear regulator design, then you want to know the ESR at the switching frequency, for example. And well, if the datasheet only indicates a value at 120 Hertz, then probably it's not very useful because, as you can see here, the ESR is strongly depending on frequency.
Yeah, that's one thing. The other thing is also the ESR has a strong influence on your loop stability. When we show tomorrow in our webinar the non-invasive stability margin, we will switch between two 10 microfarad capacitors, one with a high ESR and one with a low ESR, and you will see directly how the phase margin changes based on this ESR. So knowing the ESR of your device over frequency is definitely something you want to know when you design a power supply. The other thing I think we should show is the capacitance itself of this device.
Yes, and then we have some questions we can answer. So I select format CES here to display the capacitance, and you will notice that we have this high peak and spikes here around the resonance frequency. And this is purely because around and above resonance frequency it doesn't make sense anymore to calculate the capacitance, so the mathematical result is wrong. So I say I want to see it from 0 farad to 0.4 millifarad, and then we can read the capacitance here, and it says 218 microfarads. So it's quite accurate. It's 220 on the device and
plus minus 10%. So pretty cool stuff, yeah. Oh, plus minus 20%. In fact, it says on the data sheet, yeah.
But it's a very good device, I would say.
Mm-hmm. Oh, there's one question about the calibration.
Okay, the question is?
It's about what happens if you perform the calibration, but you do not connect the load. For example, you press the load button, but you do not connect the load. Well, in this case, still the calibration will show that the calibration has performed. Therefore, it's very important that when you have performed the calibration, you connect the load, you connect something you know, like a 100 ohm resistor, and you see if the reading is correct, because then you know that you have done a correct calibration. Then you put in a short, and you check if the short indicates the correct value, and you make an open. So this is quite important, because if you have, for example, what's the name now? Keysight? Yeah, I always say HP because I'm an old guy. So if you have a network analyzer of one of these companies with many names, and you connect, you perform a load calibration, and and you don't connect the load, it will still calibrate, and then you have the mistake as well. So that's a common problem in general with vector network analyzers. Therefore, always after you've done the calibration, use something you know, put it in, and check if you get a correct reading. Then you know that your calibration has performed correctly.
Mm. Yeah.
Yeah. Thanks a lot for the questions. Just feel free to post anything. Best thing would be to post it to Bernhard Baumgartner, because Florian is doing all the talking except for now, and I can read the chat.
Okay. Good. So the same thing we have seen before, and we will now switch to the next method, and that's the external bridge method, or the external coupler frequency suite mode in our software. And this one you can use with custom measurement bridges. So you can build your own measurement bridge, or you can use a directional coupler with an external amplifier, whatever you want. And then you calibrate at the output of the bridge with open, short, and load, and you can measure impedance. An example for this application would be to measure very high impedance values. So we have built a custom bridge, and you can see the bridge here in this circuit diagram. And there is also an application note on our webpage that explains the details and how to use the software with that. And this bridge is optimized for high impedance values, so you can measure up to, let's say, nearly a mega ohm. So we have a device under test prepared for that. It's a capacitor with very low capacitance. You can see it on the left-hand side. It's a 470 picofarad capacitor. And yeah, shall we do the measurement? Bernhard?
Yeah, for sure.
Okay. So I will again bring the camera on screen, and Bernhard is now removing our impedance adapter and connecting our custom bridge. So it's just some BNC connectors and some resistors inside.
Yeah, we have built this bridge for antenna measurements, where you also have to measure out of band reflection, for example. And there this bridge is very nice because you can measure up to high impedances.
Yeah, I didn't know that.
So, and yeah, the first customer was Transradio in Berlin for former Telefunken Sendertechnik for medium wave applications. So they got this bridge.
Perfect. So now I will switch to the external coupler mode, and that's the mode we need for this measurement. And then we need to do a calibration again. So I will resize. Or to simplify it, this is also a very nice thing with the Bode 100. You can always store your measurements and load them again. And they will include calibration and everything. So I have already done this measurement. I will now load the file. So I say open. And I say external bridge example. And if you want, you can also get these files afterwards. Of course, the calibration won't be valid for your setup, but the settings are the correct ones.
Mm-hmm.
Okay. So I was lazy. Perfect. So, and now I will start a sweep. And we can see that the sweep starts at very high impedance values. At 100 Hertz, this capacitor shows an impedance of nearly 3.3 or 3.3 mega ohms. So this is quite high, and you need special bridges to do a measurement like that with the Bode 100.
Yeah, with the impedance adapter, you would see already quite some noise in this area when you measure this capacitor. So this bridge allows you really to measure at capacitors at low frequencies.
So we'll now directly display the capacitance value, and we go up to 2 nanofarads, and we get the result here. You can see in the beginning where we have these 3 mega ohms. There we have quite some noise on the curve because this is a very high impedance for this measurement method. It's not designed for mega and giga ohm impedances, but still we get a value that looks trustful, and it says 480 picofarads. If you go a little bit higher, at 1 kilohertz, for example, it says 476 picofarads, and it's a 10% 470 picofarad capacitor. So
yeah,
everything looks
in
fine.
the range, yeah.
The capacitor itself, as you can see, has a very high self-resonance frequency, above 40 megahertz. So we don't really see it. It's quite, I would guess, close to 40 megahertz, 45, something like that.
Yeah.
Okay, perfect. So let's continue. These were the direct measurements, and we will now talk about indirect measurements.
So when do you need indirect measurements? You need indirect measurements when you want to measure either impedances which are much lower than the impedances that you can measure with the direct methods, or if they are much higher than you can measure with the direct methods. And there we will introduce several different methods to you. First of all, what are we doing with these indirect measurement methods? The reason why we call them indirect is because we measure a gain and then translate the gain into an impedance or a reflection, no matter what. In this case, into an impedance. And so the key difference is that the settings are in the gain mode. So measurement is gain, and then we choose a format, magnitude, and phase. If you choose magnitude and phase, you will get the basic impression. Then depending on the method, you will have to do some calculation to get your final impedance. The methods we are using are also quite some known methods, and this is the advantage of the Bode 100, since it's a vector network analyzer and a frequency response analyzer at the same time. So we can use the shunt through and series through methods that were introduced by HB, now Keysight, and these methods can be also done with the Bode 100 exactly the same way. The big advantage we have is that we can start at really low frequencies. So we can really measure from 1 hertz to 40 megahertz, while usually devices start at 3 kilohertz or at 300 kilohertz, depending on what you have, and you can go to the gigahertz range. Nevertheless, the customers we have are people that are in the lower frequency areas, like power supply developers and so on, and as a result, you can use these methods to determine the behavior of your components exactly in the frequency range you're working in. So you see the shunt through and the series through method, and then further on we have the possibility to measure voltage and current. As you know, the Bode 100 always measures a ratio between channel 2 and channel 1, and so in this case we can measure the current that goes through a device under test, and we can measure the voltage which is at the device under test. And since we're measuring channel 2 divided by channel 1, we measure voltage divided by current, which is impedance. So these are the indirect measurement methods, and we will start with the shunt through method. This method derives the impedance from a standard S21 VNA measurement. So we are using a VNA measurement immediately when we are just using the output and the channel 2 of the Bode 100. This is a very accurate method below 10 ohms. It goes down to a few milliohms, so it's your best choice for ultra-low impedance measurements, and it's available for the full frequency range. For sure, uncalibrated measurements are possible because you do not have an adapter, and again, the Bode 100 performs an internal calibration when it's booting, and as a result, you can already have a good situation, a good calibrated device. If you want, you can perform a true calibration prior to measurement, so to influence the impact of cables and probes. So the shunt through method is by simply connecting the device under test between the inner conductor and the outer conductor of the cables which connect the output to channel 2. And the formula to convert the complex S parameter S21 to the complex impedance of the device under test is done by this formula. We do not explain where this formula comes from. There are papers available from many people on that, but this is how it's in the literature. And for frequencies below 10 kilohertz, it might be needed that you use a common mode transformer to ensure that you don't have any problems resulting from outer conductor currents, the currents that run through the cables. And so we will start with the measurement. We configured the Bode to measure the S21 by terminating channel 2 with 50 ohms and to select gain. And so this is the example that we will now measure. We will measure a 5 milliohm shunt resistor with the Bode 100. And I hand over to Florian for this measurement.
Thank you, Bernhard. We will again bring the setup on the screen. So yeah, so you can see that we have soldered this shunt resistor between two BNC connectors. It's directly from the center conductor to the shield conductors. So that's the shunt through connection, as you have seen it before, and it's just placed now between the cables. And I will restart the software such that you can directly see what I need to set up. So I say Bode Analyzer Suite, start the Bode Analyzer Suite. It takes a moment to start the software. And here we have the software. So as mentioned before, we need to terminate the channel 2. So I start the device configuration and I click on the switch at the 50 ohm resistor and I say OK. So then the channel 2 is terminated. Then I say I want to start at 10 kilohertz, 40 megahertz, logarithmic sweep. And I want to have more power because this is a very low resistance measurement. And I reduce the receiver bandwidth a little bit to get less noise on the curve. And then I say trace through the same measurement, but I need the phase because this is a complex result and we need both values. So the blue trace now is the phase. So that's the result now. That's not the result, but that's the gain result. So that's the S21 parameter of this setup. And if I want to translate that to impedance now, I have to calculate this formula with S to 25 times S to 1 over 1 minus S to 1. And these are all complex values, so it's quite tricky to calculate this. And therefore, I use an Excel sheet and to do this calculation. So I've prepared this Excel sheet here. To bring the data from the Bode analyzer suite to Excel, I use the right-click copy trace data function. And then in Excel, I right-click and say paste the data. And the first line is only the naming, so I don't need the first line. And then it draws. Oh, I pasted it in the series through, that's wrong. I have to do it in the shunt through. Okay, but that looks better. So here we already see a diagram that shows me the impedance magnitude. I will resize it a little bit. And we can see that it says at 13.9 kilohertz we have
6 milliohms.
6 milliohms. So it's a 5 milliohm resistor, and we are measuring 6 milliohms. So we are probably an ohm off, a milliohm off, which is not a lot. And you can see that with this measurement, you can measure down to very low milliohm values.
Yeah, and we did not calibrate, so maybe this also has an influence due to the contact resistances that we have for this measurement.
Yeah. If you want to know now the series inductance of this shunt, and that's probably the reason why we want to do this measurement, because everything else you can do in DC. You can measure 5 milliohms in DC, that's not the problem. You can do it very accurately there with a high current and getting some milliohms of voltage, millivolts. Then you can measure this very precisely, and you will get 5.1 milliohms or something like that. And the reason or the advantage of our measurement is that we can see what happens over frequency. So we see that the magnitude of this shunt, the impedance magnitude, tremendously increases with frequency. So here we already have 100 milliohms at, let's say, 1 mega ohm here, 1 megahertz here, 10 megahertz here. So this would be 6 megahertz, something like that. So at 6 megahertz, it has already 100 milliohms. And if you are doing, if you want to measure high frequency currents, then you need to take care about this. So from the results, we can calculate the inductance. We use the resistance at 10 megahertz, where we have purely inductive behavior, and we'll calculate 2.55 nanohenries from that.
So we got a question that says, could the shunt impedance measurement calculation be done by the Bode suite instead of using Excel? Definitely, this is something we have on our wish list for future releases. As you know, we are continuously working on improving the Bode analyzer suite, and we are actually thinking about a so-called impedance mode, where all the measurements that we are showing today are combined together. Nevertheless, this will take some time because at the moment we are working on an improvement of the automation interface for some industrial automation applications, but this is definitely in our pipeline. So in the meantime, unfortunately, you have to use the Excel, but as you have seen, it's a simple formula, and therefore it's definitely something we want to build into the future release.
Okay, so another possibility would be the series through, which is the same method. It derives impedance from S to 1, but this time it's useful for high impedance values. The setup is similar, but the device and the test is now not connected in parallel, but in series, and the conversion formula is a little bit different. The next method I would like to outline is the voltage current gain, and as Bernhard already mentioned, this method measures gain with the external reference of the Bode 100, and then the Bode 100 measures the voltage at channel 2 divided by the voltage at channel 1, which then equals the impedance if you connect a current signal to channel 1. The advantage of this method is that you can use it for in-circuit measurements. You can use it to measure the input impedance of a power supply or the output impedance of a power supply, where you have high DC components. The only thing you need to manage is to somehow modulate these DC values with the output proportional to the output of the Bode 100. So if the Bode 100 puts out 100 Hertz, then you need to bring this 100 Hertz signal somehow into your circuit. And this is then a different story, but the measurement itself only measures the gain from channel 1 to channel 2, which then equals the impedance. It's possible to calibrate this setup if you use a 1 ohm resistor and you connect both probes to this 1 ohm resistor. Then you can perform a through calibration. Through means 1, 0 dB is 1, and then you will compensate the, for example, phase shift of a current probe or a gain shift of the voltage probe, whatever.
Yeah, you compensate, in fact, the entire frequency curve of both probes.
Yeah.
So you flatten the curve, so the influence of the probes is totally removed. And this is the cool thing, that you can do this with just a 1 ohm resistor connected to the output of the Bode 100, because since in this calibration both probes pick up the same voltage or the same signal at the same point, you can remove all the influences, and then you just go to the point where you want to perform the measurement, and you measure exactly the impedance.
Okay, but now we will go to another example, which we promised in the previous webinar, in case you have attended. We will now show you how you can measure the DC voltage sensitivity of a ceramic capacitor using the one-port impedance method and DC bias blocker or DC bias injector. In this case, we use the Picotest J2130A.
Okay. We got a question from a participant that is asking, is it possible to use a high impedance voltage probe connected to channel 2? In principle, you can connect any probes, like a 10-to-1 probe or 100-to-1 probe. You can connect differential probes. The only thing is the Bode 100 is not providing any supply voltages for probes. So this means if your probe requires a supply voltage, then you have to provide the supply voltage separately from an external power supply. We are usually, for our measurements, we are usually using standard 10-to-1 or 100-to-1 oscilloscope probes. The Bode 100's input impedance for channel 1 and channel 2 can be switched between 50 ohms and 1 mega ohm. So when you switch to channel 2 to 1 mega ohm, then you can connect the standard oscilloscope probe, which is a high impedance probe.
You have always have to be aware of that that you reduce what you want to measure if you use 100-to-1 or 10-to-1 probes. So you will always measure more noise in case you use external probes.
But the good thing is, since you can perform a calibration, as we have shown before, the influence of the 10-to-1 probe is removed. So you do not have to take this into consideration for your calculation. So that's the important part. If you use probes, always perform a calibration, and then the influence is reduced. The only exception is if you would use directly identical probes for both channels, then in some cases calibration is not necessary, like we have shown in our last webinar on the loop gain measurements for power supplies.
But with this gain measurement, the advantage is that you can always check the calibration. If you use the setup from before, if you use this setup, you can check if you get the 0 dB and 0 degree line. If not, then you can add a calibration. If you get it, you don't need to calibrate.
Okay.
Okay, so we'll now go into this example.
So we have 5 minutes left. No, we have enough time. I hope you stay with us. We have set up this session, and now you need the DC bias injector. Hold on.
I think we didn't do this measurement yesterday, so I need to search the components. Both are gone. Der Picotest Koffer. Nimm schon aus dem Kopf.
So, here we are. For this measurement, we are using a DC bias injector, which allows us to inject the bias signal to the output signal of the Bode 100. So we are combining the Bode 100 output signal with a DC voltage that we provide via a power supply. So we just connect BNC cables to our power supply. And so this is in fact already the setup to be done. And for sure, the next step is to do a calibration to calibrate this setup. I will connect a load to the and I perform just a simple open short load calibration at the output of the DC bias injector. The only thing I have to take care is that I do not choose a DC voltage that kills my load when I perform the load calibration. So we switch to the Bode software, and here we go to an impedance measurement. We choose magnitude for channel 1 and for trace 1, and we choose phase for the second channel, and now we perform a calibration. So we go to probe calibration, and we start with the open. So nothing is connected to the DC bias injector at the moment. So I will now we will now connect the short. We press the short button. We connect the load, and we press the load calibration. And now the next step is that we keep the load connected, and we just press OK, and we check what we get, and we're using a 50 ohms load. So what we get now is a nice flattened line at 50 ohms. I can activate the cursor. So we see 49.998 ohms. So we are 2 milliohms off. Now at the moment it's accurate, and we see a phase shift of a few millidegrees. So this is totally fine. And now we will connect our device under test. So Florian has just connected a capacitor, a ceramic capacitor.
You have to start at the lower frequency.
Yeah, no problem. I'll start at 10 Hertz.
Or 100.
Or 100 Hertz, whatever. So measurement has started. And now what we can do is we can switch, for example, instead of looking at the magnitude, we are looking at the capacitance itself. And we first check if the capacitance is okay. So this is seems to be a 10 microfarad or something like this capacitor.
It's a 10 micro, yeah.
And at the moment, the voltage we are adding is
zero.
Is zero. So we have no voltage. And I will store this to memory.
Maybe
and I make this in 2 diagrams. And
switch off trace 2, I think we don't need.
Okay, we don't need trace 2. So and I will optimize this. And
maybe enter 0 on the minimum then.
Yeah. So and 11 microfarads. So maybe 50 as a not 50 farads, 50 microfarads. So this is how the curve of the capacitor looks like when there is no voltage connected.
And what we can now see very nice is these bumps. And the bumps you can see here, this is caused by the probe calibration. Since this bias injector has a capacitor itself in it, and we are measuring at very low frequency now, the capacitor already has a high phase shift. And so it's not linear anymore. So we would need to do a user calibration to overcome these bumps. But for now, since the time is running out, we just can mention that these bumps are caused by the probe calibration, and that the correct values are always at the low points, so at these at the lower points of the bumps.
Okay.
But we can also go to a higher frequency where it doesn't matter anymore. So what I will do now is I will activate a voltage and load the capacitor, and you can see that the capacitance has dropped now. I've now added 4 volts to a 30 volt capacitor, and the capacitance is now at, what is it?
It's 8 microfarads only. So in fact, I can put this to memory, for example. So we have this as a curve for 4 volts. I can also give this memory a name so that we can remember this. And now we go back and activate data and memory. So now you can, usually you always have to wait a little bit when you apply voltage because the capacitor needs to charge. And yes, this is also a thing to be taken into consideration. We said it's 4 volts. The DC bias injector has some loss, so you can also, to check it, you can also measure directly at the component. And
in addition, Bernhard, what we see here is the aging of the capacitor. Because I have soldered it just right before, a second before I did solder it. And if you solder ceramic capacitors, you will de-age them. And then you are in the fastest aging process in the beginning. We are in the first second now. So what we see here now is also the aging of the ceramic capacitor. And so this is something we recognize when we have done this measurement, that the capacitors, the ceramic ones, if you solder them, you de-age them immediately. That's why it had 11 microfarads, a 10 microfarad capacitor. And now it's aging. So if we increase.
Yeah, let me do a new storage. So I've started now in the aged area.
And now I go to 10 volts, or let's say 15 volts, which is half the nominal capacitance, half the nominal voltage.
Yeah, it's going down.
So now I'm at 15 volts.
And you see, 15 volts, you only have 3 microfarads. So this is definitely something to take into consideration when you're using ceramic capacitors in your design. For example, for this, using it as a load capacitor. We once had a request from an aerospace industry where the people said that the loop gain measurements they do not fit the simulation, and they were using a nice linear simulation tool. And we contacted Linear, and they said, no, this simulation tool is working correctly. And in the end, we found out that they are using a full ceramic capacitor where the capacitance dropped really from 100 microfarads to about 10 microfarads at the output voltage they were using for their power supply. So as a result, this is a very important thing, and therefore this measurement is something to be done. As you see, this capacitor is rated for 30 volts, but at only 15 volts you already have 2.5 microfarads out of the 10 microfarads this device should have.
Okay, Bernhard, thank you very much. And that's it from our side. So in case you have any questions, you can ask them via the chat function, but since we are already quite out of time, if you have long questions, just send them to info@omicron-lab.com. But we got one, I think.
We have some minutes left on our webinar time, so we can go through these questions. One question is the capacitance drop so significant only for X5R or X7R as well?
As far as I know, X7R should be better, but it's not very good. So I have already measured X7R, which also drops not that strong as X5R, but X7R also drops significantly.
Yeah. So if the manufacturer is not providing this value, if the manufacturer of the capacitor is not providing this information in its data sheet, then we highly recommend to do this measurement. Otherwise, you might get quite some surprises when you use the capacitor.
Then we have another question. Could you write an application note with detailed information on how to measure input and output impedance of power supplies? And that's a very good topic, because tomorrow we will show how to measure output impedance of power supplies. The webinar is called the Non-Invasive Stability Measurement with the Bode 100, and there everything is based on the output impedance of a power supply. And input impedance, yes, we want to write this application note since a long time, but somehow we didn't find the time. But next week we will start doing measurements on input impedance, and hopefully next year you will get, in the beginning of next year, you will get a nice application note on input impedance.
Yeah, you can also mention that this application note is written in cooperation with the Word Corporation. Word Electronics. So we already got the demo board for this measurement, and we will measure the input impedance of a power supply with different methods. So we will use the indirect voltage method that was shown earlier, where we use a current probe, where we use a shunt resistor and the device in the test. However, we will use a different device. Instead of the BWIT100, we will use the so-called line injector, where we can inject a voltage directly onto the supply voltage of the power supply. And the second method we will do is we will do a method with a current probe, as shown on this slide. So again, here we will use the line injector, and this application note, I hope that it will be available in the first quarter of next year from our side.
I think so.
Next question, is it necessary to have a current injector to measure output impedance of a switched mode power supply? Well, as always, it depends. The current injector we are using is, what you need is you need to be able to modulate your load. Yes. That is the requirement. You need to add an AC current to the DC current that you have at the output of a power supply. And this can be done by modulating the load. We recommend to use a current injector because there we have a good high rise time, so we can really sweep up to high frequencies. And further on, it is a clearly defined load. It's not a capacitive load. It's not adding any capacitance to your load, to the load capacitance of your power supply.
However, you can, if you have very low voltages, you can also use the shunt through method. But the Bode 100 is not designed for DC voltage, so everything above 3 volts DC can be dangerous to the Bode 100. So then you need to have current injectors or DC blocks or whatever. But there are many possibilities to measure output impedance. The current injector method is just the one that is very convenient.
Yeah, absolutely. In fact, you know that the current injector came into existence because I learned that someone is measuring directly connecting the output voltage, the output of a power supply to the output of the Bode 100, and performed the one-port measurement and said, oh, come on, if you go above 3 or 4 volts, you possibly kill the output op-amp of the Bode 100. And so the current injector came into existence. Okay, so if there are no additional questions, we really thank you for participating in the webinar, for staying with us. We apologize for the glitches that happened in the beginning. For example, me running out because someone had no sound of our peers that we had logged in. Thanks a lot for staying with us for an hour. And we have more webinars upcoming tomorrow. We have 2 topics tomorrow. One is non-invasive stability measurement of the power supplies. And there we measure the output impedance of a power supply. So if you're interested, just click in. Everybody should have received also the login data for these 2 sessions tomorrow. Yeah, second session is a special session where you have the chance to see the WDS software of Bias Digital and how it can be used together with the Bode 100 to design power supplies.
Yes. Okay, thank you very much, and in this case, I wish you a nice day, and maybe see you tomorrow.
Okay, and by the way, we have a recording. We will save it and make it available on our webpage after the webinar to all attendees. And for sure, you're allowed to share it with your colleagues. Thanks a lot. Have a great day.
Goodbye.